Yeah, no, it's fine. Okay, 2 minutes more. Let's wait for 2 minutes, and I'm dropping an email anyways. Okay, 2 minutes, and let me drop an email anyways. So okay, so let's start. Last time we discussed still connected components, and we were supposed to start centrality measures for nodes. So we were starting node centrality measures, and is my screen iPad screen visible? Okay. So yeah, anyways, I'll start from start again. So node centrality measures. So there are most commonly used 6-7 node centrality measures. Okay, so the most commonly used and the easiest one is degree centrality. So first of all, I'll explain where degree centrality is used because these questions might come in exam in applied part. Okay. So first of all, they are used in essential protein detection. There is a study, if you search Google Scholar, Tang et al. 2013. So it in protein networks using degree centrality, essential proteins are detected, and in online settings, in online setting or you say social media, degree centrality is used to detect most influential users. So they are usually found to for marketing purposes, whom to give sponsorship, whom not to give, etc. etc. And yeah, today's lecture might be a bit long, so we might take a break at 7 and then at maybe 7:15. So please bear with me because these concepts, at least 4-5 questions will be coming. Okay, so yeah, so degree centrality, as I told, degree centrality is computed for a node. It's not computed for a graph because these are node centrality properties. Okay. So the formula for degree centrality, this D means degree centrality, degree, this C means centrality, and this V is the node for which we have to compute the degree centrality. I'll explain each term one by one. Okay. So this V is a node. This V is a node for which we have to compute the degree centrality. These are all the nodes present in the network because the graph is represented as G, V, comma E. This V is all the nodes which are present in the network. We take all the nodes, we compute their degrees, we select the node with maximum degree, and we check compared to the node with maximum degree how much degrees does a particular node has. So based on that, we determine whether this node is say there is a node which has degree 40 and this is the highest degree max, and you take a node with degree 30. Okay, so the ratio, that's CDV, will become 3 by 4, which is equals to 0.75. So what you can say is this node V is 75% most influential, this node contains 75% influencing power compared to the most influential node. Okay, got it till now? Hi Sushma. So last time, whatever I discussed, I was just revisiting those concepts. I think you were there, Sushma. You were there, right? Am I audible? Hello. Okay. So yeah. So you can, as you can see, what I told was, so there's a node V with degree 30, and maximum degree of a node in a network is 40. So what we can say about node V, we can say V node has 75% influencing power compared to the most influencing node. That is correct, because if user, say this is K, is able to influence 40 people at once, this is able to influence 30 people. That is basically the degree centrality. I have written all these things, and why is this degree centrality measure used? Okay. Anyways, and I'm discussing use cases together because last time we were in hurry and I was not able to basically start this properly. So use cases, because these application questions, as they came in assignments, they will come in exam as well. And don't forget, we have another session for revision on 20th of October. So the next Sunday is 6 plus 7, 13th, then 20th. Yeah, 20th. I don't think so. There's Sunday. I don't know. I think you will get an email before that. Anyways. So next thing is closeness centrality. So obviously it's represented as C, closeness of node V. Okay. So let's discuss the applications first. Applications of closeness centrality. If you guys have any doubts, just raise your hand, or just you can unmute yourself, because there are not a lot of there are not a lot of people, so you can discuss the doubts here as well. Okay. So closeness centrality is used to measure extent of information spread. Okay. Extent in the sense means this is somewhat similar to degree centrality only, but it basically deals with not the number of I would say not exactly the number of nodes. It deals with the shortest path connected to the nodes. Okay. So what happens is, it might be the case you have a very high degree, but this means the say the distance between this thing, distance one nodes are say 30. You have very high degree, but distance two nodes are very less. Okay. This means you have a detachment thing. Okay. So what when I say this thing, why does it matter? Because it might be the case that, okay, you are good at influencing people, you have a lot of following, okay, but you are connected to this main network here. This is a main network, okay, and it has a lot of nodes. Although the degree is not very high in this network, but say this is the node, it has degree 20, and this node has max degree, this network has max degree equals to 5. Okay, but this network has vertices equals to say 500, but here the vertices are only 20. So degree centrality is basically used to target, is used in market campaigning, etc., etc., because they want to check the direct audience. Because, okay, I am watching an advertisement from some people, from some sort of influencer, but that doesn't mean I will be advertising the product in return. It's the responsibility of that influencer, because that is taking up the money. If I am getting influenced, I'll buy it. Okay, so this is why degree centrality is important in such cases where direct contact is necessary. to influence decisions. But this is not true. See, this node is not close to the network. Okay, how close a particular node is to the rest of the network. So this node is not close to the network. It has very high degree anyways. But if I start comparing paths, so for 20 nodes, its distance is 1. But for other 500 nodes, its distance is greater than 1. Okay, so it will be around greater than equal to 2 maybe, or maybe 2.5 at an average, whatever it is. So this node cannot be used to basically spread information, not in sense to a lot of people. Okay, I'm not saying till the last end of the network, but it won't be able to spread information to this node even, because this is getting path from here and even to this node. Okay, so yeah, this is why let me just describe this here. This is why closeness centrality comes into picture. So we measure the extent of information spread using closeness centrality. Hmm. So the formula for CCV is, I'll just explain the formula. So we take a node V, we calculate the distance from V to all the nodes in the network, and obviously if the distance is quite high, this means that the node is not that influential in that network. Okay, so that is why we make it reciprocal, because high distance means it has a very less closeness centrality, it's not close to the network, so we make it reciprocal. And to normalize it, we add this V minus 1 because V is already a node here which is taken into consideration. The remaining nodes are V minus 1. To make the computation simple, people generally use V only, but when we have very high number of nodes, so it doesn't matter, you can use V minus 1 for application purposes. But in exam, if the question comes, you have to use this exact formula because the answers will be matching this formula. Okay. The next thing, yeah. Oh, sorry. Now is it fine? Cool. Okay, so the next thing is betweenness centrality. I think we were here last time and we couldn't start it. So anyways, I'll just explain it first. Before going to the explanation, I will just explain why betweenness centrality is used. So there is a concept called articulation points. Okay, to explain this concept of articulation points, let me, there's a web series on Netflix, that's Kala Pani or something like that. Okay, so it's basically about an epidemic that breaks out on an island on Andaman and Nicobar, and ultimately it spreads to the whole of Andaman and Nicobar. So the government basically contains that island, air support, water support, everything is contained. So somehow 1 or 2 patients break out from that to the mainland, the main Indian subcontinent, and then their season 2 might be coming up, and that will tell how the disease will spread. So those 2-3 people which broke out, they are articulation points, okay, in a network. So articulation points are a point which, if removed, can disconnect the whole network. So there's a concept of connected component. Okay, so I'll tell you. So if I remove this node and I remove from a picture, will this network become a disconnected component? Well, I mean, will this network break into 2 parts? No, right? Will it? Anybody tell? Just type here. Hmm. Exactly. Exactly. Okay. So then there is, say, this, I have this other component here, and this node connects this component. So if I remove, say, this node, I'm not breaking the link. I'm removing the node at all itself. Okay. If I remove this node or this node, okay, this will break the network into two parts. Correct? Am I right? Just you can type here yes and no. Okay. If like it's not possible to unmute yourself, you can type here. I just want to know like you're getting the point. Okay. So I'm removing this kala pani stuff. It's not needed. So you can see this network has one articulation point, or one articulation point generally consists of two nodes. It does not consist of one node, because that's a link. Articulation point is generally a link, and you do not compute these centrality measures for a link. You compute them for nodes. So articulation point generally contains two nodes. And if any one of them is removed, the network gets disconnected. So I'll tell you how do you find which one of the two should be removed. Okay. So betweenness centrality of node V is computed as so what is this formula? Can anyone tell? So this basically tells the for this is for all x and y belonging to V. Okay. Where x is not equals to V is not equals to y. So you see, they have taken two nodes here to check for articulation points. Okay, you take all the nodes in the graph. I say I take this node and this node, then I take this node and this node, this node and this node. So it is a n square complexity thing. Okay, for like says it will be computed like a adjacency matrix, and you can see in the book there is a figure that is basically similar to adjacency matrix. If you are able to see, I'm not sure, you will be able to see it here. This example is not relevant anyways, I'll tell you. Okay, so what does this thing measures? This thing is saying take all the shortest path between x and y, number of shortest paths between x and y. So length of shortest path will be one. No, sorry, there will be only one shortest path. Correct? I mean, not one shortest path. There will be shortest path, multiple shortest path, which will have the lowest number of length. So say if the length of shortest path is 2, but there exist six such paths. So between x and y, there will be six such paths. Then this thing represents shortest paths, number of shortest paths between x and y, which contain v. Okay, basically passing through v. So you don't have to, you cannot take paths which do not pass through v and which are shorter. You will have to take longer paths which pass through v, which must pass through v to compute this betweenness centrality. Okay, getting it? Cool. So Yeah, that's how you compute this thing, this edge between the centrality. Just a second. Then there are multiple variants of edge centrality, like edge between the between the centrality. So there is edge between the centrality. There is flow between the centrality. These are just variants, and I think they are not part of curriculum. So I think they are. Have they been taught in the class? Edge betweenness, flow betweenness. So basically, flow betweenness says you take all paths instead of shortest paths. Wherever the flow takes. Edge between the centrality refers to the fraction of all pairs passed through a given edge. So they basically tell, so this x, y should be u comma v. So this is the shortest path between x and y such that they pass through this edge. Okay, so instead of computing it for this node and this node, you compute it for this edge combined. So that is how you compute it for the articulation point instead of individual nodes of the articulation point. Okay, that's what I told in the start. Articulation points are two nodes. So this between the centrality is used to compute it for each individual nodes, but this edge between the centrality is used to compute it for both nodes. Okay, so that is why this is important. Yet it won't be asked in the exam. Numerically, it might be asked in definition manner. So what is it? Which one of it uses an edge to compute centrality measure? Okay. So then answer will be this edge between the centrality. Then the most important thing in this chapter is page rank, etc. is there, but I feel eigenvector centrality is an important topic. So is there anyone who can explain to me what is eigenvector centrality? Anyways, it's a revision class. I hope you guys are preparing for the exam. Anyone? Just a small description, one line description. What does eigenvector centrality do? What others could not? Okay, I'll explain. But anyways, I'll ask this page rank and card centrality from you. So be prepared from whatever notes you have. I'll ask it. Just a second. So eigenvector centrality measures the importance of node. By taking its neighborhood, by taking the preference of its neighborhood, the preference of its neighbor. So basically, a node's importance is determined using the local neighborhood. So that neighborhood may not be the ego network neighbors, the immediate neighbors, the alters. The alters, they may not be just alters, they may be the second order neighborhood, say second hop, third hop neighborhood. Anyways, so eigenvector centrality, just a second, is mostly used in websites. So Google, basically Google uses PageRank, which internally uses eigenvector centrality to basically give you top searches. So whatever you see on Google, so if there's a page that is directed, that a lot of pages refer to, okay, that is basically authority in PageRank, and that is the best. So that will have a high neighborhood number, high number. So that is where this PageRank, eigenvector, this all thing is used. CAT's centrality is also there. Anyways, I'll just explain it one by one. So eigenvector centrality of a node V is measured using this way. So you have 1 by lambda 1, then you have summation, you take T, T is the neighbor of V, okay, and you take the eigenvector similarity of this T. So you give some initials similarities to the nodes, okay. So say you have given some initial weight to initially to some nodes, and then you compute it for all the neighbors. So this basically works iteratively for all the nodes, 1 hop, 2 hop, 3 hop, like that. This can be also written as 1 by lambda 1 summation a v comma t. This is adjacency matrix, and this is xt. So this is done for all the t belonging to network V. So if there exists the value a v comma t equal to 1, this means there exists the value, and if this value exists, this means this xt will be taken for that node because it will be the neighbor, and that is how this formula comes up into picture. I think it's quite simple. Anybody, any doubts? So if you write it in matrix form, it just looks like this: ax is equals to lambda x, like this. You can bring this lambda here, and this is the matrix form of this thing. That is how it looks like. So any doubts till now? Any questions? I'll explain how this thing just gets adapted in CAT centrality and PageRank. But till now, any doubts? So this is nothing. This is just weighted average of this eigenvector centrality of neighbors. And initially there will be something given. So say 0.1 is given to nodes with degree 1. The 0.2 is given to nodes with degree 2. So you can initially you can use say degree centrality can be used as initial eigenvector centrality for all the nodes, okay, and then iteratively you can check. So after 5 epochs, after six epochs, how does it affect, okay. So this lambda 1 is nothing. This lambda 1 is an if you see the so this is how this equation is written, and this lambda 1 is computed like this. So this is how this lambda 1 is computed. Lambda 1 is the largest eigenvalue after solving this equation. So consider you take degree centrality as initial eigenvalues, so and you put it here and you solve for lambda 1. So lambda 1 will give you the highest eigenvalue, and then since it is giving the highest eigenvalue, so Whenever this summation etc is divided by this thing, it gets normalized in that range. Okay, any doubts? So cat centrality. Can anyone tell me what is cat centrality? Sushma, do you have any idea? Hello. Okay, anyways, I'll just start because we have a lot of things to finish. And since we have a lot of things to finish, I'll just take up important concepts because I don't think so we'll be able to finish in 2-3 classes. I overestimated my capacity to teach. Anyways, so till now, what we have seen that eigenvector centrality, I will write this at xv. xv uses immediate neighbors. But what's the problem with immediate neighbors? Immediate neighbors might be limited. Okay, consider you have just 3 immediate neighbors, but that doesn't mean you don't have that much influence, because those 3 immediate neighbors can be influenced by a lot of previous neighbors. So cat centrality takes others neighbors into consideration as well. I'll write the equation first and then I'll explain. So I've told in the start that adjacency matrix, when we do it square, it becomes 2-hop representation, 2-hop neighbor representation. When do it power k, it becomes k-hop representation of neighbors. Whether the kth neighbor is connected or not, whether I comma j is kth neighbor or not. Okay. Then this alpha k is here attenuation factor that basically decides. Just a second. So you have that this basically decides for what k is the iteration, basically first iteration, second iteration, third iteration. So you sum it together for all the iterations. So assume you want to take it for k is equal to 3. So you want to take it for 3-hop neighbors, till 3-hop neighbors. So you take 1-hop neighbors, you take 2-hop neighbors, you take 3-hop neighbors, and you do sum. So there will be sum 1, there will be one sum that will be j equals to 1 v alpha 1 a j comma I plus summation j equals to 1 v alpha square a j comma I plus summation j equals to 1 v alpha cube a j comma I. So what this basically tells is, you take immediate neighbors, you take some value of alpha, that's power 1. For all, so for card centrality of ith node, you take all the nodes in the network, you take 1-hop neighbors, because if there is 1-hop relationship, this value will become 1, otherwise it will become 0. Okay, and then you multiply it by alpha. Then for 2-hop neighbors, this value will become 1. For all other nodes, it will become 0. So you take for 2-hop neighbors. Okay, then you take all for all 3-hop neighbors, and this alpha basically is a number from just 0 alpha 1. So when you square it, when you cube it, it automatically keeps on decreasing. So it basically decreases the effect of further neighbors, but ultimately cat centrality takes n-hop neighbors or k-hop neighbors into consideration. So this is just an improved version of eigenvector centrality. Any doubts? Okay, I'll finish page rank. So I have already told that eigenvector centrality, cache centrality, page rank, they all are used for the same purpose to find the most influential web page, etc. Because it has been redirected by a lot of the pages directly or indirectly. Okay. So I'll just write the formula for page rank first. So you have a node vi. Can anyone explain this formula to me? So first I'll explain this thing. So this is in. So in vi tells this is a set of nodes vt which point towards vi. It will look something like this. And these centralities, these eigenvector centralities, these all centralities are measured for directed graphs. Okay. Because then only this thing matters, this relationship of pointing like to other web page, etc., etc. So this is vt, this is vt, this is vi. Okay. So what we do, I'll explain this part later. Let me explain this part. We take the page rank to compute the page rank of this thing. We take the page rank of vt of all the nodes divided by out degree of vt. We want to check, apart from pointing to this node, what other nodes does it point to. Okay. So once we compute it for all the neighbors or for all the pointed nodes of vi, we apply this d. D is a damping factor. We reduce its effect. Okay. And then we add this term as well. Okay. So consider there is no node. There is no node that points to vi. Does it mean it will get page rank 0? No. It should have some page rank value. So that page rank value is determined by this factor here. Okay. So this page rank value is basically 1 minus damping factor divided by number of nodes. This is allotted to all the nodes initially which do not have any this in vi, this set, the length of this set is 0, then this page rank value is allotted to them. It is also allotted to nodes which do not, which even have something, but we cannot leave these nodes like high and dry. So we allot them this page rank value. So whenever this question is asked, what is the use of this? So this basically tells a probability of jumping to this page. So basically what is page rank value? Page rank is a probability of jumping to a page on internet. What is the probability that a random node will jump on that page? So I will tell, yeah, this when there are no invert connections, this probability is 1 minus d divided by number of nodes that are randomly you can jump to this page because there are no invert connections. So these values are generally quite low compared to the initial page rank other page rank values. So as you can see, the first term 1 by d upon mod v is the probability of random worker starting a new work from a random node. Okay, so this is what the exact thing tells. Any doubts till now? Any doubts? Okay. Sorry, screen locked. Last time I didn't upload the PDF. I'll upload it today because I didn't have a lot of notes to share. The next thing we have is uh, just a second. Week 9. Just a second, let me open it. Huh. Yep. Okay, just a second, let me check one thing. If the answer is even correct or not. Because from week 8, 9, 10, these assignments were not made by me. Just stay on the line, okay? Week 9. Okay, the answer given is proximity based approach only. So let me ask. Okay, I'll ask and I'll post it in the discussion, group discussion. Okay. Uh, so common neighbors basically does not fall under structure based, I think. Only Adamic Adar falls under structure based. But Adamic Adar also falls under proximity based because you're comparing the common neighbors here. In Adamic Adar, that is basically like Jacquard similarities type of thing. So that also depends on proximity. It's not structure. Sorry, common neighbors is not structure based. So it is asking which lecture, which video. Mm-hmm. No, wait. I'll see it. Okay. Uh, yeah. Where is it exactly? See, if you open it at 6 minutes 19 seconds, you will see that structure based approach is internally has feature based methods and proximity based methods. Okay, so common and dynamic Adar, they fall under proximity based. They are structure based, but in fine grained level, they are proximity based. Structure based is right answer, but it's for common neighbors it's not structure based. No, for dynamic index, it's structure based is correct. Common neighbors does not basically depend particularly on structure. It depends on proximity. Neighbors are proximity. Your proximity is only. Hmm. Dyadic, dyadic, dyadic is feature based. Dyadic is feature based. Okay, my iPad is got disconnected. Just a second. Any other doubts? Just a second. It should be given in the video. What is given in the video? Okay, let me find it. Okay, I'll find it. I'll send it there because I have not seen this week 9 thing. I was supposed to, but let me. I can check it right now. Like 4 5 minutes. I can. And let me check. It might be in week 3. Sorry, lecture 3. Okay, I'll have to search it. I'll just leave it for now. It might take us some time. I'll share it on that discussion group. The next thing, which we were on page rank. So the next thing, which is quite similar to page rank or in degree or out degree, is Hubble authority. So page rank basically does not measure the in that out degree thing explicitly. So we just tell like how many pages point to a page, but we cannot tell if that page points out to a lot of pages. So that is why we use this hub and authority. So hub node V, hubness of node V is basically taken like this. So we take the nodes which have out, I'll tell you, let me write the formula first. Okay. So node V has node V points out to these nodes and we measure the authority of these nodes. Authority means what else nodes point out to this node to compute the hubness of V. Because basically say you have a node V that is say Wikipedia type of thing. So Wikipedia references to a lot of pages. Okay, so it has a very high hubness. But if those pages to which Wikipedia references are not visited by other pages, are not linked by other pages, this means those pages are waste because Wikipedia, instead of giving those links, the people might not visit those pages because they are not linked anywhere. So ultimately, they will, if they visit Wikipedia, then only those pages can be visited. This means if person visits Wikipedia, then only that person can visit the page outside Wikipedia from that Wikipedia, and not from outside easily. This means that page does not have a lot of weightage. It is just given for reference purposes. It doesn't mean anything. So this is why hub and authority are basically reverse of each other. Authority of V is U in degree of V. This is hubness of U. So they are just opposite of each other, and we measure this thing to compute the outgoing power and incoming power of each page. Okay, this very simple measure, doesn't require a lot of stuff, a lot of mathematics to understand. Then there is assortativity, an easy concept, yet it is asked quite a lot, and it might be asked this time as well. So assortativity is based on the formula I was saying, that a man is known by the company it keeps. Okay. So assortativity checks, if we think of friendship network, then like-minded people often become friends. Okay. And ultimately they share some common characteristics. They share some common characteristics. So in the sense they might share some common intellectual power, common physical strength, etc., etc. So assortative mixing is the measure based on principle that two similar nodes have high preference for each other. Preference for each other means affinity. Affinity means if these two nodes are brought together, they will automatically get connected. Okay, it doesn't matter whether they haven't met for a long time, but if they are similar, they will automatically get connected. So assortativity is measured using a lot of things, but generally scientists prefer it measuring using degree or say common neighbors, and most of times it's Pearson correlation coefficient is used. So there's say R xy, n is the number of, so basically when Pearson correlation coefficient is used, it uses sampling and distribution. Whenever this thing comes up, automatically start believing there's some sampling going on from some distribution, because you cannot measure Pearson correlation coefficient statistically for the whole data set, because the whole data set is infinite in size. So this is some scientific statistical lingo. So this n is the number of samples in each distribution. Then x and y are the degree distribution of nodes. Okay. Then this degree distribution of x and y individually. Then this whole thing is just written in that manner only. And of summation of x square minus summation of x whole square, this whole thing times and of summation of y square minus summation of y whole square, like this. Mathematically It's like, it's not in exam. There won't be any question to solve or compute assortativity, but there will be a question that how does assortativity comes? How do we compute? So we compute it using sampling some distribution and then computing Pearson correlation coefficient. Okay, this question will come if Rx comma y is equal to 1. This means samples are perfectly assortative. If Rx comma y is minus 1, then it's perfectly disassortative. And when it's 0, it's non-assortative. Okay, this is a very basic thing. Yet this thing might be asked. Perfectly non-associative, this thing. Okay, so just try to remember the whole concept behind it. You don't need to compute. You don't need to memorize anything from this. Then there is trans. Mhm. So you tell me how minus 1 will come here when this thing is less than product of this thing. True, because this will be always positive. This will all. No, they are completely in opposite direction. So I will explain it in context of Pearson correlation coefficient. Okay, so Pearson correlation coefficient is 1 when data points lie like this. Okay, then it's plus 1. Okay, when data points lie like this, there is a negative relationship between them, then it's minus 1. And when the data points are some randomly spread in some place, there is no relationship, then it's 0. Okay, so these are basically feature based metrics. So x and y basically can come from the degree distribution. They can come from degree distribution, or they can come from whatever feature you want to use, whatever attribute you want to use. Okay, so yeah, this is it about that. And then coming to these concepts are very basic. I won't go into the formula. I can go into the formula part, but anyways, let's study them properly. There's no time. There's no sense just wasting time on. Okay, just a second. I got a new. Okay, so what is transitivity? Transitivity means if there exists a link from A to B and there exists a link from A to C, so there should exist a link from A to C, correct? So social network also, if A is a friend of B, B is a friend of C, there is a high chance that A is also a friend of C. Okay. So when a this is important thing, when a network has high transitivity, what can you say about the network? Transitivity. What can you say about the network? It is heading towards being a complete network. I take this graph here. A, B, C, D. A is a friend of B, B is a friend of C, A is also a friend of C. B is a friend of C, B is a friend of C is a friend of D, but B is not friend of D. So if I connect this, then B also becomes friend of D. Then C. Or I can say A is a friend of C is a friend of D, but D is not friend of A. So if I try to complete this transitive property, then this network tries to become complete network. Complete network. Okay. So this might be a question in exam, that the network which has high transitivity, what does it indicate about the network? A high transitive network indicates what property about the network. Okay. So it's very simple. You can see. The next thing is reciprocity. Let's take a 2 minutes break, okay? I'm going to have some water. You guys, please stay. If you like, don't leave this thing. You can just go and come back. I'm thirsty right now. Yeah, I'll be back, okay? Okay, so my Google Meet is updated, getting updated. Just a minute. On my iPad. Yeah, now it's updated. Am I audible? Cool. So yeah, let's start. Till now we have studied transitivity. So then there is reciprocity. So reciprocity is generally applicable in directed graphs. Doesn't make sense in a directed graph because if there exists an edge bit from A to B, then there also exists an edge from B to A. Okay. So if a graph has high reciprocity, what does it tell? Can anybody tell me what does it tell? Sushma? I won't go into the maths of reciprocity. I can actually, it's not that difficult, it's very easy. But what does it tell about reciprocity? If there's a very high reciprocity in the network, you can unmute yourself and tell. So high reciprocity means if an edge exists between A to B, then exists between B to A. This means it's a strongly connected component. Okay. So if a graph has high reciprocity, it means it is headed towards strongly connected component. Because what is the definition of connected component? You can travel from one node to any other node through the help of edges. But in directed graphs, the edges have directions. So if you want to use the directions of those edges, then we use the term strongly connected components. If you don't want to use the direction of edges, we use weakly connected components. Okay. So a strongly connected component is a directed graph which has paths from one node to the other node easily, like direct paths are there. So it means it's still not a strongly connected component, but it is headed towards strongly connected components. So say there's a this network A, B, C, D. If I have this edge, can I go from A to B and B to A? Yes, A to B, A to C, C to D. Can I go from C to A? I cannot because this edge is not present. So I will add this edge. So now I can go from C to A. Can I go from come from A to D? But I cannot come from D to A. So even if I connect this edge, so it's simple. D to A I can go. I can go from C to A. I can go from B to A. But it's still not a high reciprocity graph because these edges not present. So that's what I said. It might not be a completely high reciprocity graph if it's a strongly connected components, but this generally is proportional to each other. Okay. High reciprocity is always proportional to a strongly connected component. So if I use this cycle thing, here, I can go from any other node. Like I can go from B to D, I can go from D to B, but it doesn't mean it's a high reciprocity graph. It's not a high reciprocity graph. It's a weak low reciprocity graph, but still a strongly connected component because it is somehow bypassing that. So Strongly connected component does not mean it will be a high reciprocity graph, but a high reciprocity graph will mean that it's a strongly connected component. Okay, it's very simple relation. So this does not mean, but this means this. Okay, so reciprocity can be easily computed. So this is the number of edges by 2. Then you take two edges I comma j such that I is less than j, and we sum this I j into j I. Okay, so this basically tells if aij is 1 and aj is 1, this means the reciprocity is of present between those two nodes. We compute it for all the nodes in the graph, and that's how we compute the reciprocity. Another method is to use the trace. Okay, trace of a square. So this is from adjacency matrix A. If I square it, this means 2 hop becomes 1. If 2 hop is there, then it becomes 1. So if there is an edge from A to B and then B to A, then this means A to A is 2 hop. So all diagonal elements will become 1. So how do we take out diagonal elements from a matrix? We apply trace operation. Trace operation on A square will give us diagonal elements of that matrix. And similarly, we use this formula 2 by E into 1 by 2 times trace of A square. Why we are doing 1 by 2 times? Because here we use this I is less than j, but here there is no relationship. So if A comma from A to B, B to A is computed, then this means B to A to B is also computed. Okay, so that's why we divide it by 2, because there are duplicates in the trace matrix. Okay, so that's why we divide it by 2. So once we divide by 2, this becomes just simple trace upon E. Remember this thing, this will come in exam in this formula or in this formula. These things will come in exam. Okay. So till now we have studied reciprocity, etc., etc., centrality measures mostly. So now let us see some of the most common similarity measures. These similarity measures can be used in this thing, in assortativity, etc., etc. Anyways, so the most common one is common neighbors. Common neighbors we all know. This is NA intersection NB. I'll just quickly go through in this whole thing in 5 minutes. But this number is graph dependent. Graphs with high number of nodes will have this value high, so we normalize it to make it Jacquard similarity. Jacquard similarity is NA intersection NB divided by NA union NB, and then there is cosine similarity. We all know it's very common. We just apply NA intersection NB, this whole thing, then square root of number of neighbors of A, number of neighbors of B. Very simple basic stuff. Anyways, this was important because this will be used in future lectures. So I'm just showing you this for now. Then degeneracy is very good concept. Can anyone tell me what is degeneracy? You all have studied. Hello, am I audible? say something, guys. Do you guys know what is degeneracy? Last concept of this chapter. Then we'll go to chapter 3, network growth model, famous Albert Varavasi thing. Okay, what I'll do is I'm leaving this concept here, degeneracy. In next lecture, we'll pick it up from here. Because we have like 40 minutes, 35 minutes are there, and we can finish some of the basic network growth models, etc. etc. And they are an important concept, so if I start today, it won't take a lot of time next class. So this will be interactive session. I want one of you to interact with me for this chapter, for this part basically. So what is the need of network growth models? What is the need for these network growth models? Can anyone tell me? Sushma? No, no, no. What is the need? Like their network growth models are what are network growth models? What is the need of these network growth models? You have a real world network, okay? You have a real world network that is very big. So say you have Facebook network that has trillions of, not trillions, trillions is a very big number. I mean people have multiple accounts, but I don't think there's an exponential number of accounts. So just stay with me. I'll keep on asking questions. So consider Facebook currently has 750 million users. This number is a bit below 1 billion compared to the population of Earth that is around 8 billion, but still. So can you analyze this type of graph easily? These many nodes, or just let me make it big. Let me make it 2.5 billion users. Combining Instagram, WhatsApp, Facebook, Threads. It has 2.5 billion users or accounts. So analyzing these accounts is very difficult. Analyzing these graphs, very difficult. I mean, machine learning can process it, but manually you cannot extract information from these types of graphs. Why? Because if you import 2.5 billion user graph in Gephi, if you import this graph in Gephi, Gephi will hang. It doesn't have that much memory, and if you start finding communities, etc., etc., it will start to crash. So we need some smaller graphs which mimic the properties of bigger graphs. I need a graph because so there is a concept of uh, graph coarsening in machine learning. There is a concept of graph coarsening, but it's a recent concept, graph coarsening, whatever the definition is. So graph coarsening basically tries to reduce the size of graph, given graph, any graph, by keeping the properties intact for study purposes. But in social network, we have graphs. So there are three properties which we want to preserve. Three properties which we want to preserve. What are those three properties? So I'll just tell you. Graphs has graphs have communities. Okay. We want to preserve the community structure. So from this two types of properties come up. That is high average local clustering coefficient and small world property. Then the third property is, yeah, scale free. You guys are typing here. Okay. You can unmute yourself and tell. Okay. Like there are two, three people. It doesn't matter. Like nobody will get disturbed here. Then the third property is scale free property. Okay. So what is scale free property? What is this? I'm not gonna ask now. I'll just explain it one by one. I think it has been explained. So three things I will ask you to study. This one thing on your end. Next Sunday when we meet. Degeneracy concept you have to study, and two three networks which I'll ask you to study. Because since you are sitting here, the rest of the people are not. So you should take advantage of this thing. So what if I'm asking you to study, then just go and study, because next time when we discuss now, we will just pick up the concepts from your memory instead of me reading from the book. Okay. So what is a high average local clustering coefficient? At an individual level, neighbors of a node tend to be highly connected with each other. Okay, so what I'm saying is, if there is a node which has a high degree, these nodes should also be connected to each other somehow. Okay, this is what high average local cluster, because ultimately what we do now, we remove these edges and we check how many edges are possible between these nodes and how many edges do they have currently. Okay, so in real world, this type of property gives rise to communities. As you can see, there is a very high chance this will exist as a community. So I want that social network community should be preserved in an artificially generated network. Okay. So this is what we call high average local clustering coefficient. Then we have small world property. There's also an experiment conducted by Milgram, Milgram small world experiment. Okay, so if you want to just Google it, you can find by this name, Milgram's small world experiment. Okay, Google it, you will find. There will be a video explaining this. Anyways, this is not important right now because we are discussing, we have short on time. So small world property, yeah, 6 hop separation between any two nodes in a network, correct. So this was proved because this experiment was done in 1967. There was no social media. So this experiment proved that local networks, I'm not talking about Facebook, big network, local networks like office email thing, office email communications, or say locality, the colony you live in, they have the average maximum average path length of 6. Okay, so small world property says that average path length of a graph Ig is proportional to log of G, log of the size of network. Okay, so this is small world property. This was Milgram's small world experiment. So if I put 4 here, or it is 6, 6 is equal to k times log of x. So for k equals to 1, log will be 10 to power 6, correct? Sorry, x will be 10 to the power 6. Am I right? Hello? So I think 10 to the power 6 is 1 million. Yeah. So for k equals to 1, if I say this k constant is 1, so 1 million people, for a 1 million people, average path length will be 6. So if I change it, I change this number, say k equals to 2. So this becomes 1000. So for Milgram, this k value was almost, the higher the k value, the smaller the graph becomes to follow this property. Okay. So ultimately, when we construct a synthetic network, we want a high k value, high value of k. Because I don't want million nodes, I don't want billion nodes, I want a lower number of nodes. So this x becomes 3 when k equals to 2, that is 1000. So for 1000 nodes, this experiment was conducted by Milgram. I think it was 296 letters something. So I think it was even smaller. For k equal to 4, it became something like that. Anyways, so high k value means smaller network will be generated. Remember this thing because this maybe I'm not saying certainly, but this may be asked. Okay. Then the third property is a scale-free property. What is scale-free property? Can anyone tell me? You can unmute yourself and tell. Correct. So because let's not go into that last property. Last property was small world property. But for average, high average local clustering coefficient, you can see there will be communities. Okay, so there will be some community leaders. They will have very high degree. So a graph of billion nodes will have 100 communities, meaning 100 community leaders, which ultimately means there will be small number of nodes with high degree and high number of nodes with low degree. This will look something like this, and this is what is called power law, or whatever this is, scale free property, you can say. Nodes with degree 1 will be a lot higher, nodes with degree 2 will be lesser, nodes with degree 500 will be even lesser, but they will be there because they will be might have part of some communities, Lady Gaga type of thing. Anyways, so just remember these three things, and then we have three types of network models. Okay, so I will just go into the basics of these network models. I will not go into the mathematics because that mathematics you obviously know is not easy to frame as a question and ask as an MCQ. So first is random network model. What if I create a random network that follows these properties? That follows these three properties. So network can be random network can be of two types. This will be G n comma k, whereas n is the number of nodes, k is edges. Okay, then the other one is G n comma p. Okay, and this is the number of nodes, and p is a probability that there will be an edge between any two nodes. P means the probability that there will be an edge. So if you go to this week 2 tout session, I have shown using coding this thing. So if you want to revisit this, you can go there. Very interesting concept I have shown in the form in Python, and this network X coding. And, in week 2 or week 3 it will be there. You can just go through the notebooks present in this Google Drive link on that portal. There's an Excel sheet, it has a Google Drive link. So you can go through those notebooks and you will find that how this probability affects the structure of the graph, how this probability affects the structure. Okay. So anyways, you can go through the formula of, I don't want to go into the formula because this is very easy. There is a proof, that proof was very important. So I will just explain that proof again, or I don't need to, because it's explained in one of the videos. So there is theorem that a giant component in random network emerges when average degree of network is greater than or equal to 1. So I have done this proof, I have explained it. It can also be found in the video. So this proof won't be asked, but it is very important proof. I suggest you go through it. But then there are two, three things like, what is this value? This D is P times n minus 1. So this D is average degree. Okay, so you have to prove that this D is greater than or equal to 1. So this means you have to prove this P n minus 1 is greater than or equal to 1. Okay. Then there's this property. These two, three things I'm telling because these are important. Pk is equal to e to the power minus d into d to the power k upon k factorial. Okay, so this is basically Poisson distribution, and this is the problem with random network, that it does not follow scale free law. It follows Poisson distribution, not power law. Okay, so if you compute average path length here, so they follow this average path length will come be close to log of n. So they follow this property, follow this small world property. They will be in question, they might be in question. This also, this random model is also known as Erdos and Rennie model. Okay, so don't get confused when question comes in the exam. And once you compute the local clustering coefficient, so this becomes, this local clustering coefficient of node I equals to P, this becomes D by N. So local clustering coefficient is inversely proportional to the size of network. Okay, so coefficient does not depend on the degree of network. But what does the high local clustering property say? That high local clustering coefficient depends on the degree of the network. It does not depend on degree, it depends on the size. Okay, so it follows just one property, I think, this small world property. It does not follow this property and this property. Okay, hello, am I audible? Yeah, so they don't follow scale free, they don't follow local clustering coefficient, they just follow small world property. So we need to create some network which follows all three of them. So then there is another network, that is ring lattice network. Again, you can find a very beautiful tutorial, like I will just tell you, in one of the previous weekly sessions. It's uploaded on YouTube. You can just go through the PDFs present. It's basically a coding video again. So you can just find the coding APYNB file. You can search it and go to the corresponding week, and you will find a very basic, very decent explanation how this thing shows. Okay, so it basically takes two things. Uh, ring lattice takes two things. Okay, so I'll explain it. So anyways, it tells that a node is connect, if there are say there are k nodes in a graph, then a node is connected to k by 2 minus 1 nodes on right, and k by 2 minus 1 nodes on left. Okay, sorry, k by 2 minus 2 nodes, because one is included here, one is excluded here. Okay, so ultimately the formula for local clustering coefficients comes to be 3k minus 2 by 4k minus 1. Easy to remember. 3 plus 2 5, 4 plus 1 5. Just remember it like this, so it's very easy to remember. Okay, so for very large value of k, when k is very high or k tends to infinity, local clustering coefficient is 0.75, which is very high. Okay, so now we have satisfied the property of local clustering coefficient as well, apart from they have already given. Okay, this follows very high local clustering coefficient, but it's small world property, it doesn't follow small world property. And power law, It also doesn't follow power law. It just follows very high clustering coefficient. So it follows these two things here. Then the third and the most important model till date is Albert Barabasi, or basically it's other known as preferential attachment model. Okay, so preferential attachment model means a node will be attached in a graph to a node which has high degree. So this looks like it follows the local clustering coefficient thing correctly. Okay, and also it follows the power law thing, because a node with high degree will only gain high degree. Okay, so it won't make the nodes with lower degrees gain higher degrees, and it won't disturb this thing. Okay, so node with degree so this graph won't become a straight line because these nodes will not jump here, because these nodes have less degree. Okay, but these nodes have high degree, so this graph won't become something like this graph won't become something like this. It will always follow this thing. It will in fact keep on shifting. So initially if it was like this, it will become like this. Ultimately it will become like this. It won't gain the shape upwards. Okay, it's very simple, intuitive to understand. Nodes with high degree, so node with degree 5 will become with node with degree 6. It won't come to this side, so this thing won't jump. It's easy to understand, right? Got it? Cool. So this is the basic preferential attachment model. I'm not going into the maths, I'm not going into the other stuff. So we have followed scale theory property here, we have followed high clustering coefficient property here, and since this network is same to random type of thing, so it also follows that property where average path length is equals to log of size of network. So it's also given as proof somewhere. You can just watch the video. Very simple proof is there. So yeah, this is all about these three models. These are very basic things, and I have told you the intuitive things from these models because the questions will come intuitively. There won't be a numerical on Albert Baramasi model. The question will be like this. So what happens to nodes with high degree? They become nodes with higher degree. That is what this is the type of questions where that will come. So yeah, we have till now covered till chapter 3. I was expecting to finish chapter. So that's all. After this, the link analysis thing, tried closure, page rank, etc. And we can finish that next week, because revision from start is important, because my guys might have forgot everything. So chapter 3 is done. What I want you guys, so homework will be this thing. Degeneracy. We will discuss it if you guys don't understand. It's very simple concept. Degeneracy. And then study the maths behind these three models. Very basic maths is there. If you have any doubts, just ask me, but I'm just skipping the maths because it will take a lot of time to grasp. But to explain it here, it 2 hours are not sufficient. We need at least 5-6 hours to just revise maths, but you can just watch such videos in 2x and finish the mathematics. So next week we will study chapter 4, which is link analysis. In link analysis we will study balance theory. So I want you people to just study the basics of this thing, balance theory in signed networks. Okay. Then there's status theory. Guys, I want you guys to study these two, three concepts. They're very basic concepts. If you guys have any confusion, strong ties, weak ties, because we have less time for revision. And if there's any confusion, then I'll just revise it. Dunbar number, local bridge, page rank is again coming up in the next chapter. The mathematics behind page rank. Till now, what we studied was basics of page rank. Now we'll study the mathematics behind page rank. Okay, so this is important. This is very important. Okay. So matrix manipulation, conversion, everything. If you guys are not able to understand, then you can ask me. And then there's sim rank, div rank. These three, four things are very important. Okay, questions will be asked on these 3, 4 things. Okay. Then the next chapter is community structure. This chapter 5. So we'll try to reach here. We will try to finish some of the concepts here. Okay. But if we are not able to reach, this is like permanence, modularity. Questions will be asked, and difficult questions will be asked from these concepts. Difficult means you will have to use calculator computation. Okay. So yeah, these are the things which are important for the exam. We have exam on 26th, right? Exam is on 26th. Okay. Exam is when is the exam? Okay. So by 19th, we have 2 more lectures remaining. In 2 more lectures, I'll try to revise all these concepts which have been taught and which might have just gotten away from your brain. So we'll just finish that content. And if you guys have any doubts, so we can visit those doubts as well. I tried to get the PPTs, but the PPTs are not available for this course. So if you guys want to revise, you have to watch videos for now. I'm sorry about that, but I'll try to ask one more time. If the PPTs are available, I'll share it by this week, by next week. That will make the revision easier. Anyways, but we don't have it. So yeah, that's that. And any doubts? Any doubts till now? Where? Mm-hmm. Well, note with a very high degree. What do you think? Closeness centrality should be the answer, right? Or degree centrality? What do you think? Degree centrality has one issue. Degree centrality has one issue. It means it deals with a lot of people directly. Okay, that directly thing is very confusing. Getting my point? So, and what is the answer? Is the answer given? Okay, let me check. Oh, what week? What week was that? Let me check if the answer is given or not. 23. 23 did not have that question. Week 3, week 3 or week 2? Week 3. Okay, let me check 22. The boss is eigenvector centrality. Boss will be the page rank, eigenvector, cat centrality, this type of thing. Okay. Yeah, it should be degree centrality only. The person who deals with most number of people. It should be degree centrality. It should not be closeness centrality. Closeness centrality is basically spreading message faster. Because even though you don't know a lot of people, those people you know a lot of people. Okay, so you are basically in somewhere close to the network. Okay, yeah. Person who deals with most. Yeah, it is degree centrality. And the boss is means basically page rank, eigenvector centrality, authority, card centrality, these type of measures. If the question comes and the option is either one of those, that is the correct answer. Okay. Okay. Chalo. Any other question? Okay then. Cool. Bye bye. Let's meet next week and discuss whatever like doubts whatever things we have studied, and whatever things I have asked you to do in homework. Study that, and if you have any doubts, we'll discuss that. Okay, that's all. Thanks a lot. Bye bye. You're welcome. Bye bye.